Okay, just a reminder, this is a silent session, meaning you've got to use your headphones so you can hear the speakers. And that's because the auditorium is being divided in two without a soundproof wall. So if you want to hear the speakers, you should grab one of the headsets up in front at the top. Well, I'm Christopher Neal. I serve as the director of the Dougherty Water for Food Global Institute at the University of Nebraska. And this session today, we're going to discuss water productivity and different approaches to measuring and estimating water productivity of crops and livestock in agriculture production. So our first speaker, what we're going to do is have 4 presentations, and at the end we can have questions. If in the time slot we have time for questions, I'll bring that up, but if not, we'll leave the questions to the end, okay? So there'll be 3 presentations and then a video presentation, as Dr. Messa McConan was unable to attend in person because of visa issues. So he will be, we have a video, and then he will be attending virtually if there's any questions for him. So our first speaker is Livia Peiser. She's an officer with the Land and Water Division of FAO, and she's trained as a geographer in spatial sciences. So she's going to give us a perspective on using technological innovations for water productivity estimation. Livia, please welcome Livia. Thank you.
Yep. Hello, good morning, good afternoon, everybody. So yes, Livia Peiser, I'm a land and water officer in FAO Rome, and I will be talking about what we do at FAO to monitor water productivity, land and water productivity, and take it to the countries we work with. So first, I'd like to give a little bit of background on why FAO and why we focus so much on monitoring water productivity. And I'll do that by mentioning some figures that come from FAO state of flagship publication, like the status of food insecurity and the food and agriculture. And from those reports, we can see that the state that's over 828 million people still suffer from hunger, and at the same time 3.2 billion people live in agricultural areas with high to very high water shortages. And at the same time we see that agricultural production still needs to grow globally to cover the demand that is expected to increase in the next 25 years or so. So that the agricultural production needs to grow globally by 50%. At the same time, we also see that the current patterns on intensification are not proven sustainable, and that is what is coming up from the recent status of land and water resources. And maybe even more importantly in all this is that almost 85% of increase in cropland extent is coming in irrigated conditions. So we have 85% of these 63 million hectares that have been added to the total cropland between 2000 and 2019 are irrigated. So that means that there's a lot that needs to be done to be able to produce more food with less water. And that's what we mean by when we talk about water productivity. And in agriculture, water productivity means that we need to be able to increase output, so that can be in kilograms per hectare per unit of water consumed, and that is cubic meter per hectare. There's different ways of measuring water productivity. There can have an economic aspects. So the output in particular can be measured in yields, in biomass, in economic return, in jobs, in so many different ways. But bottom line is that we need to be able to measure what value we are able to get from the water we are consuming, and how we make sure that we are increasing the value that we take from the water that we are using, but in particular consuming. So that's the focus that we want to give, is not necessarily on the water that is abstracted, but on the water that is consumed. So evapotranspired, and that means that is water that is not available anymore for other uses in the same domain. So that is the definition, let's say, in agricultural water productivity is yields per cubic meter of water consumed. But unfortunately, measuring these two variables is not easy at all, and particularly if we think of the common measuring tools that we find in the countries we work with, like this flow meter here. So that's why satellites can really help us in this effort, because they can provide information, data that through which we can monitor water productivity in cost-effective ways. They do not replace completely, of course, field-based observation and other types of monitoring, but they are a very good supportive tool, particularly when it comes to measuring water productivity over large areas and over time. And in addition to that, and also thanks to these technological advancements, now monitoring water productivity and increasing water productivity is now a globally recognized target, and is very much aligned to SDG 6, and in particular 6.4, for which FAO is custodian agency of two indicators. So that's why that's another reason why FAO has been working in developing an operational methodology to monitor water productivity using satellite data. So that's what we do. We started with the support of the government of the Netherlands, but now many other donors have joined forces. We work in close collaboration, partnership with IHE Delft Institute and the International Water Management Institute, and also when it comes to data production with eLeaf company. We use open access satellite data, and from those calculate key land and water variables such as biomass, evaporation, precipitation, and so on. And based on these variables, we calculate water productivity indicators and water accounting. So as I showed in the previous slides, with biomass and evapotranspiration, we are able to measure the outputs in biomass per cubic meter of water consumed in agricultural areas and in all land areas. Then we publish all this data on through an open access data portal. That's the Vapor portal that you can find on the FAO website. If you Google for FAO Vapor, you'll find it. And on that portal, you'll find every 10 days, so in near real time, data on biomass development, water consumption, in addition to other agroclimatic parameters such as reference CT, precipitation. We produce the data currently at 3 different levels of resolution, because this type of data has different types of application, from a field level where farmers can use the data, to more policy-oriented application. So at the moment, the whole of Africa and the Near East is covered at 250 meter resolution, and a good number of countries, more than 20 countries, are covered with 100 meter resolution, and some selected irrigation schemes have even higher resolution data, because that can be used for monitoring field level practices. this is what you see here is one snapshot of the database covering Africa and the Near East. But then there's high resolution areas. This is one example in the Jazeera irrigation system in Sudan that shows the level of detail that we get with the data 30-meter resolution. So in this case, for example, the map you see here shows actual evapotranspiration over a decade. And you can just click on a point and get the time series. So be able to calculate the water consumption of, in this case, can be cotton, wheat, or other crops. We also have a lot of, we put a lot of efforts in making sure that the data that we produce is open access data, is described in methodology, and the codes, underlying codes and algorithms are fully available and provided as open source, so that researchers and practitioners all over the world can test it and hopefully as a community improve it over time. So everything is distributed through the website, and the data is also distributed through API, and that means that it can be integrated into existing portals and applications. And everything is following, of course, open geospatial standards. And in addition to that, we just published the methodology on a wiki page that is easy to navigate, and there you can see how each different layer is calculated with what input data, what satellite input data are being used, and what parameters and so on. And lastly, to document properly and the methodology, there's also a Python application, Python implementation of the calculation. So that's if you would like to test to calculate it yourself or over an area that is not yet covered, you may try to do it yourself. Of course, that requires a good understanding of Python, but also remote sensing and water. But we are happy to assist. So that's for what concerns how we publish and document the data. And then I'll just mention very quickly what we do in terms of offering capacity development, and what type of applications we can develop with the data. So in terms of capacity development, I'll just mention a couple of online courses. There's on the website, you can find very many online courses, mostly developed by IHE Delft, that can help understanding the data. And also in this case, through this course that was launched last June, also understanding how hard it is, let's say, to validate and to understand the quality of the data and the concepts behind quality assessment and validation, and then do it yourself. So this is an online course that can be followed for free on the IHE Delft platform. But there's also one specific course that I just like to mention here, because the session is on water productivity. So there's a MOOC that was developed by IHE Delft and partners on water productivity in practice. So understanding what are the different aspects of water productivity, the biophysical, but also the economical and social aspects of water productivity. And that is also available online. But I'll just close by mentioning a few, 2 or 3 examples of applications of the data, or how the data is being used. And as I mentioned earlier, because the data has different types of potential applications depending on the scale, and the users you can find applications that are made for farmers or end users in general, so that the data from the portal is translated through smartphone applications and other types of devices to provide advisory services to farmers, or, for example, advisory services in countries. There's also another level that is more at the irrigation scheme level or river basin authorities that can use the data to monitor the performance of irrigation systems and make decisions on the water allocation, for example. And on different levels, it can be also used to monitor, for example, SDG, water allocation strategies, and so on. So I'll just mention a few of them. So one that might be relevant for this audience is a study that was done in collaboration with the World Bank and the FAO Investment Center. And in that case, they also wanted the focus there was on monitoring water productivity of wheat in the Bekaa Valley, wheat and potato, and then also looking at the economic incentives for improving water productivity. So with the vapor data, they were able to first select the wheat fields and calculate the yields and the water productivity. So the map that you see on the left is the map of yields in a given season, and on the right is the water productivity. And as the legend shows, that there's in the Bekaa Valley, there seems to be higher yields for wheat in the southwest part of the valley, but when it comes to water productivity, there's higher water productivity distribution in the northeast part of the scheme. It's not a scheme of the valley, and I wanted to highlight that because I think that is important to monitor at the same time the land and the water productivity, because farmers are in most cases interested in getting high land productivity, so yields, and while water let's say policymakers are more interested in the water productivity. So you need to be looking at both together. So that is something that you can also do in this case. In this scatter plot, we plotted the yields and the water productivity of these wheat fields. And it is clear that there is a scope for increasing water productivity in high yielding fields. So, for example, if you in this case, that's the square that is highlighted in the scatter plot is already filtering yields that are above 5 tons per hectare. So in that square, there's room for improving water productivity, and that's exactly where policies can look at and understand why some farmers are performing better than others, and learn from them and design incentives and systems for improving water productivity in the same area. So that's there's more. I mean, I will not go into the details, but another advantage, of course, of using remote sensing is that you can do that over large areas. So this is an example of application done in Sudan in the Jazeera scheme. It's a huge system. So with remote sensing, you can highlight areas of low and high water productivity throughout the scheme, and that helps targeting interventions. And the data, as I mentioned, can be let's say ingested into smartphone applications that can then be used to provide advisory services to farmers. And this has been done also in collaboration with DIMI. This has been done in Egypt, for example, and in Lebanon, and in other countries. It's on the way. And I'll another application that is, let's say, more straightforward is being able to monitor water consumption directly. This is an area in the Office du Niger in Mali, where the irrigation scheme managers had issues had troubles in monitoring water consumption in the newly developed sugarcane part of the scheme that is in the lower part. So with remote sensing information, we can now understand and measure the water consumption of the different parts of the scheme over time. So that's it in the time I was in the short time I was given. I just wanted to raise your your interest in this open data, and get back to us if you have any interest in using it. It's just also would like to mention that the global coverage of the database is expected to be available in October. and that we're also working to expand the collaboration with partners, including with the EU Copernicus system to ensure the longer-term sustainability of the system. And if you would like to know more, just please join us. We have another session on this topic on Thursday at 11. So that's all for the moment, and thank you all.
Thank you, Livia. We'll hold the questions to the end then, and move on to our next speaker, Dr. Abdul Karim Saeed. He works for the International Water Management Institute and located in the Addis office of the Nile Basin in Addis. Please.
Can you hear me? Okay. Thank you very much. IMI, International Water Management Institute, partners with FAO, especially in applying, testing the WAPO data, especially in Ethiopia and partly in Sudan. Now we're not working in Sudan because of the security situation. Otherwise, we have some experience working with WAPO data. So my presentation really focuses on especially like to look into how can we move from research-based applications more into operational applications of satellite remote sensing data for monitoring crop water productivity, and all the applications we can work on using that kind of data. Right. So this is a brief outline of my presentation. First, especially here, I'm focusing on smallholder farmers, and especially in the context of small-scale irrigation projects. In many sub-Saharan African countries, the smallholder farmers they make the bulk of the rural, farming households, and at the same time, because of climate change and other reasons, there is expansion of small-scale irrigation. This kind of farming system, they have unique features, and so they are really significant in terms of, in the context of food security for the countries. And IMI works on this area, especially increasing the climate resilience of smallholder farmers in Ethiopia. And so at the same time, because the plot sizes are usually small, and most often the water that is being used for irrigation is not monitored. There's very little infrastructure. At the same time, there's huge potential because of the size of the number of the areas covered by small-scale irrigation schemes and smallholder farmers. And there is a potential for expanding use of this kind of data for monitoring productivity, but enhancing water use efficiency as well. So that's where I focus. Or the picture you see on the right-hand side on the slides show proliferation of pumping systems for irrigation. The upper picture shows you in the Lake Tana Basin, one of the rivers, there's a lot of diesel pumps being used for irrigation. The farmers irrigate cash crops, and because of the income, they generate income, they can afford to pay for the fuel. And water abstraction is not being monitored, and at times it leads to drying up of rivers. So monitoring of water productivity, but also also in addition, actual water use in agriculture is absolutely important for more sustainable agriculture water use in the smallholder sector. In Ethiopia, certainly, but I also expect this to be the case for the rest of Africa, sub-Saharan Africa especially. So this is a slide which I brought from Libya, and water productivity here is just kilogram of output, sometimes biomass or crop yield per hectare, and per unit of water. All right. So what's really important here is the actual estimation of the yield or the biomass, for example, and whether we are talking about the biophysical productivity or whether we are talking about the economic or social productivity. But also important is the actual evapotranspiration, which is really very important, because the actual ET is the measure we use to determine how much water is being used by the crop. And in most of sub-Saharan African countries, there are very little data, if at all, to validate the actual ET data. So it means basically we have an estimate of actual ET, which is usually not validated really. So for this reason, the accuracy really is very important. As we think of like moving into more operational application of satellite-based estimation of agricultural water use in general, not only productivity. We have some experience in applying the WAPOR data. In Ethiopia, what you see here is applied, WAPOR data applied in the KOGA scheme. KOGA is part of the Blue Nile scheme. It's actually an irrigation scheme with 7,000 hectares of irrigation, which is being managed by the farmers themselves, right? So in this study, we use the WAPOR data on one side, but also like field measurement of soil moisture, using some instrument, the chameleon sensor, and the wetting front detector, specifically to advise farmers when to irrigate and how much to irrigate. All right, that's really a project which was completed a few years back. We have now the second phase of the project. So what you see on the left-hand side is the gross biomass productivity on the left-hand side. And then what we call the beneficial fraction of the ET, which is transpiration divided by the actual ET. So where you see distinct patterns between the upper, and the downstream end of the canal system. So in this study, actually, there was a very visible insight that information assisted crop irrigation scheduling makes a lot of difference. And then WAPOR data can help really seeing the spatial variation of productivity at the same time crop water use as well, which would help in making sure actually we have a better water management system. I think similar results was shown by Olivia earlier in the Bekaa Valley, I guess. So this kind of spatial, identifying the hotspot areas and then really identifying further the root causes would help us in a better management of agricultural water. So these are some of the examples, again, from the KOGA study, which showed by providing information and advices to farmers, it's possible to enhance productivity, right, up to 25%. But again, of course, it all depends upon availability of water. And this WAPOR data was really useful in identifying the spatial patterns of productivity at the same time, also the actual water used by crops. Right now, we are using in Ethiopia again the WAPOR data under the phase 2 of the project to strengthen what we call the irrigation management information system for Ethiopia. This is IMISET, which is a comprehensive database system which provides specifically different types of indicators for managing irrigation in Ethiopia. And among it, the agricultural water use is one of them. And the water use efficiency is another one. So WAPOR data is being used because I've said earlier, there is a lack of actual measurement of water withdrawal, especially in the small scale irrigation sector. And for this reason, how much water is being used by the crops and how much is really applied on the fields is not available. So the WAPOR data is used to estimate that. At the same time, in order to validate this time round, we are working with the Ethiopian Ministry of Agriculture in Ethiopia, which has already commissioned the Ethiopian Institute of Agricultural Research to do some kind of field data collection on about 70 irrigation schemes in Ethiopia. The idea is really to validate some of the data to help feed into the MSS system on one side, but also really to validate the baseline water irrigation water use efficiency as well. So we are working together with that one, with the Ministry of Agriculture. The other application right now is on understanding key drivers of wheat productivity in Ethiopia. Wheat now is a big agenda in Ethiopia. So there's a huge government push to expand wheat production in Ethiopia. So this is going to be, we hope it's going to be to provide very useful information to the government in especially planning, because right now there is a massive scale expansion of wheat farms. And with this, using WAPO data, we are trying to identify really which are the hotspots and which are really key drivers of wheat productivity. And what factors need to be considered? Where do we really need to grow wheat, for example, with good results? So this is going to be another major application. It's just at the beginning, but it's going to be a major application in Ethiopia because wheat has become such a big agenda for the government. Now, the question now for me is look, we have already some good results, which still pretty much, as far as I know, in the region where I'm working at a research level. So the thing is, to make really a big difference, we need to move from research to more operational application of this type of systems. What I mean by operational application is when it's mainstreamed to government planning process, for example, into government monitoring process, or in the use by the private sector, for example. That is really important because at research level, we have isolated results here and there. So in thinking, when we think about those, some of the challenges we need to overcome. One is, for example, having good resolution data or a large area. If you talk about Ethiopia, for example, or East Africa or Sub-Saharan Africa, now the question is, we have some good data, especially 30-meter resolution of WAPO data, for example, for limited areas in Ethiopia, I know, around the Awash Basin, part of the Awash Basin, the Koga region, which is part of the Lake Tana system. But I mean, we have mainly at certain country level, we have under 100 meter resolution data. But if you are talking about small scale irrigation or smallholder farmers, usually many of the land holdings are less than 1 hectare, which is 100 by 100 means 1 hectare, basically. So, improving the spatial resolution over a large area, which is very important because we're talking about countries, all right, not only specific regions. The other one is lack of capacity. Outside the academic research institutions circle, there's still lack of capacity for using. When I talk about capacity, it's not only the know-how, there's also the issue of like the hardware, the software as well, which is also very important. Then land use, land cover mapping is very important because these are also dynamic. They change from year to year, sometimes from season to season. One of the challenges we are facing for the wheat productivity study we are doing right now is having an accurate map showing where the wheat production areas are, which farms are really growing wheat in a particular season, because changing from season to season. And that is absolutely important because especially we are talking about crop yield, not only just the biomass production, and then the land cover map becomes absolutely important. Then, of course, as I've said earlier, actual evapotranspiration is the big unknown generally. So with very little validation data on the ground. So having some ground in situ data for validating actual evapotranspiration is absolutely important, which is also a big challenge. In the absence of that, where we assume it is correct, but it definitely has some its own errors within it. No. So talking about scaling, some of the parameters which I want to talk about are one of the spatial, the temporal scale, for example. So you're talking about the past trends, which will help us to understand, to prioritize, for example, interventions, for example, which ones really are hotspot areas in terms of production. The other one is season. For example, today, We have the near real-time data on vapor, for example. So is it possible to project for the season, for example? In many of our regions, for example, in Ethiopia and South Africa, drought is a big phenomenon. So there will be weather forecasts every season. Can we somehow convert that into a likely, probable, productivity map, for example, and to alert government or emergency, services to be prepared for, the kind of emergencies you may have? That's one question. The other one is the spatial scale, farm scale and catchment scale, for example, or basin or national scales. These are important. Although we are talking about spatial resolution, but why I'm putting the spatial scale as an issue is having the data over a large area is very important if you are talking about operational application and mainstreaming it into the different institutions, government and private sector. So with this in mind, maybe I have a couple of points for discussion. Some of my recommendations, for example, is the huge capacity development, effort need to be done here. It's not only the technical skill and the know-how, but the hardware, the software. Maybe I might want to mention at this point, some people might know the Digital Earth Africa program. We have the Digital Earth Africa program, which is a big program with the objective of making analysis, satellite Earth observation data available to African institutions. So Digital Earth Africa have been running for quite a number of years now. IMI works with Digital Earth Africa. So they have a catalog of analysis-ready data. Can we think of, for example, data like vapor data being part of the Digital Earth Africa, for example, initiative, which makes it available to a wider, audience, right, in Africa. But at the same time, the Digital Earth Africa is not just a repository of data, but has also tools and scripts, for example, which users can use. It's not exactly the same model like Google Earth Engine, but somehow similar, especially in making available data on one side, but also making available tools on the other side for users to handle, but also like storage resources on the Amazon Web Service, and also like processing time as well. That's a major problem for many African institutions. So when I talk about capacity, it's about, of course, the human skills required is important, but also the hardware, the software, possibly using like the cloud services provided by the Digital Earth Africa could be one way. Then the other one is very important really is we need to go out from research into mainstreaming it into or embedding it into workflows of relevant government agencies. Ministry of Agriculture, they plan, they estimate yield, they sometimes even forecast yield, for example. What is the possibility, the prospects for using this kind of tools in their workflows, which is important, which makes it really useful, which makes it also more sustainable. As we have more users, there'll be more demand for improvement, there'll be more demand for the tool, and that could be another way for if you want to really scale it. The other one is I talked earlier. The farm size is an important issue because many smallholder farmers, the farm size are really small, sometimes smaller than the resolution we have, or especially if you are talking about 100-meter resolution. So in Ethiopia, there's a drive to what they call it land consolidation. So a group of farmers making their land, their farms being made seamlessly contiguous from one farm to the other farm. This is a cluster, all right? That could be one possibility we can leverage, for example, to use. Then awareness raising on the potential huge communication campaign is very important for government agencies to know the potential of this. Then private sector role. There are many private sector companies coming up in Ethiopia providing agro-advisory services. Now, these kind of tools are important. IMI currently is working with private sectors on this avenue. Then probably, as I have said earlier, the data need to be refined, to be validated, to be improved. Maybe let's think about learning watersheds or learning landscapes where we can have more intensive ground-based in-situ data collection, which will supplement the satellite-based data collection. And together with that one, we continuously refine the data, all right? And at the same time, that refinement will also benefit the applications elsewhere. So these are some of the thoughts I have for discussion later on. I thank you for your attention.
Thank you, Abdul Karim. Moving on to the next presentation. And I happen to be the speaker on this one. As I mentioned, trying to load it up here. Oh, there we go. Water for Food Global Institute at the University of Nebraska. My training is in civil and irrigation engineering. And I'm fortunate to have had Livia and Abdul Karim speak before me because they've touched on some of the technical issues related to estimating water productivity. I'm going to focus on some work that we did in Nebraska. Just to give you a little background, we are the state in the U.S. with the highest irrigated area, 3.5 million hectares. 92% of that is pumping from groundwater. You see on the map on the right, the High Plains Aquifer, and Nebraska is blessed with the thickest aquifer, deepest portion of the aquifer in the recharge zone. And if you look down below, over the last 15 years, irrigation application has been dropping for a variety of reasons. One is a conversion of surface irrigation to sprinkler irrigation in center pivots. And the other is that the farmers are doing a better job managing their water as well with center pivots. Nebraska sits on a transition zone. If you look on the upper left of the map, we're in the semi-arid zone, 400 millimeters per year of precip. And on the southeast lower right-hand corner, we're up to 900 millimeters. So there's a huge transition of precip in the state from semi-arid west to the rain-fed east. And in a normal year in the eastern part of Nebraska, you can grow soybeans and corn with natural precipitation and be very productive. The map on the right shows that big red area, which is the sand hills, where sand dunes covered with short grass prairie, like the Hollywood movies where the buffaloes roam. Right, that's the sort of landscape. It's also an important recharge area, and the 4 agroclimatic zones shown there. You can go online to see the report we published in 2019, the Nebraska Water Productivity Report, where we looked at crop water productivity and livestock. That triangle that you see on the right is what we call the golden triangle. We grow corn, rain-fed and irrigated in the state. That is used to produce ethanol, a biofuel. And the subproduct of the ethanol production, what's left over after fermentation, is the distiller's grain, and that is fed to the cattle in confinement. Okay, so the cattle and water productivity will be discussed by Mesfin in the next presentation. But you can dig into that report and download it and read the details. As our previous speakers has pointed out, there's different ways of identifying or defining water productivity, and that's always been a criticism in certain people. But I want to make clear that we are using in the Water Productivity Report the same definition that Abdul Karim and Livia have shown, which is the yield, the amount of grain or fiber divided by the water consumed, in this case through the evapotranspiration process in the field. But there's other ways of defining, and I'll come back to that in a little while. So we use the aquacrop model. Okay, divided the state in 1,375 grids, and There's a rich climate data in the state with multiple automated weather stations, soil maps, crop data layers, maps of irrigated area. This is something that Abdul Karim brought up. The land use maps are important if you want to separate rain-fed from irrigation. And then the county statistics on yield and productivity that is kept by the counties and provided to the U.S. government. So if we look at how water productivity of corn and soybeans, which were the two crops that we looked at in detail, has increased over 25 years, you could see almost doubling of the water productivity in this time span. Most of this, if you look at the lower graphs, are due to the increase in yield. Okay. And that's because of the high producing hybrids that have been developed by the different seed companies, right? That change the structure of the plant. I mean, if you go into a cornfield now in Iowa and Nebraska, the corn is all erectophile, the top part of the canopy. It's been bred to be that way instead of planophile. And that allows more light to do photosynthesis with the lower leaves, and they can increase the planting density, right? And more plants per hectare ends up being more yield, right? So that's one of the mechanisms that have been bred into these varieties to increase the productivity and the production, and therefore the water productivity as well. Okay, as I mentioned, the ET is what we use, the water consumed. In the report, you'll see these maps separating irrigated corn and irrigated soybeans and rain-fed, and how the water productivity varies in that gradient of precipitation in the state. Remember, as you go further west, it's drier, and you need irrigation to have a economically viable crop. In the middle of the state, if you're a smart farmer, you use the precip to the maximum advantage and supplement with irrigation. Looking at the gaps, so the gaps are not very significant. Most farmers are doing a fairly good job. Obviously, the gaps for irrigated corn and soybeans is less than the rain-fed, because you have control over the water and you can irrigate when there's a hot period or flash drought or something like that. But this shows you that gaps are not very significant for both of these crops. So a summary of this report, the irrigation application has dropped. Yield of water productivity of both these crops have grown. And there's room further to increase, especially in the denominator part of the equation, right? On the consumption of the water through the ET process. There's still room to be more efficient in irrigation. Now let's bring in remote sensing to this, and this has already been brought up by our two other speakers. We're using the FAO 66 aquacrop approach, where we are using the normalized water productivity. Abdul Karim named that a different term, but it's the same term, right? It's the transpiration divided by the ET, or water consumed. And then in the end, you estimate the biomass and you use the harvest index to get the yield, right? To transform that biomass into grain or fiber. We also have a model called SETB, which is the spatial ET modeling interface, and we use satellite imagery, thermal and multispectral imagery to run an energy and water balance. But on the right side, the water balance using the FAO 56 approach, we're estimating the actual ET and maintaining a water balance in the root zone. And we're using remote sensing to get to the basal crop coefficient, which is the transpiration portion of the ET from the crop. So we use the soil adjusted vegetation index, not the NDVI. We used to use the NDVI, but the SAVI has some advantages. And we use Landsat imagery or different platforms. And here's a study that we did in a publication where we looked at biomass and water productivity approach and yield using the aquacrop and using evapotranspiration measured with towers, flux towers at ecovariance. And so this is the approach, and the normalized water productivity is where the transpiration coefficient, or the KCB from satellite and SAVI, comes in. And a study applying this, Nebraska has 23 natural resource districts that manage groundwater locally. You can go into our website to learn more about this system. But we did a study in 3 natural resource districts, and the one in purple up above in the north end of the state is in the sandhills, sandy soils, only center pivots. And the other 2, Central Platte, the one in green, is along the Platte River, more silt loam, and the yellow one is clay loam soils. So these fields have different water holding capacities that you see in the table below. Obviously, the sand in the lower Niobrara holds less water in that 1.5 meter root zone depth that we were assuming, while the silt loam and the clay loam holds more water. But here's the results of our modeling of what we consider the irrigation versus the observed irrigation. And here's another advantage of Nebraska. It's very data rich. Each one of those irrigation wells has a meter, okay, totalizing the amount of water that's being pumped by the farmer. So we have a good measurement of how much the farmer is applying on that field, so we can compare our estimates against those. And you could see over here on the left the huge scatter in red dry years, even in wet and normal years. And that's because of surface irrigation, right? There's a need for applying more water when you're applying water through surface irrigation versus center pivot. If you looked in the lower top graph, which is center pivot in the tri-basin in lower Niobrara, you see a lot more behaved. But even in the Central Platte, some center pivots are applying over 1 meter of water. Wow, that's a lot of water, right? And so these are farmers that we can go and work with, identify, and have extension work and understand what's happening at the farm field level, and why do they have to, and why they need to pump so much. But this gives you an idea of the type of research we can do, and here's some averages. And in all cases, surface irrigation through furrow applies more water than our estimates of the need, even considering the application efficiency, which we do in our model. So looking at water productivity of these fields, you can see in the table above, in general, the yields are large in Nebraska, 12 to 12.5, 13 tons per hectare of maize. Though that's the average value. Some farmers get, 16, 17 tons per hectare. So these are highly productive fields. And down below is the water productivity. Now, careful here. Here's the definition that is different, right? We're using the total water applied and used in that field, irrigation, precip, and water storage in that top series of graphs. And down below it is just the increment of irrigation over the rain-fed, right? So just a different way of looking at water productivity. But in all cases, you can see that the center pivot irrigation is greater than the furrow irrigation, and there's potential then to still increase the water productivity in these systems. And of course, we can get estimated yields spatially with the remote sensing and get spatial water productivity in the fields. Here's the example in a couple of center pivots, and you'll see the figures down below, which are the spatial values of water productivity. So one area that still needs to be addressed is we're using the harvest index, as I measured, to convert the biomass to grain. And here's an example of comparing actual yield with modeled yield in these fields. And red is 2012, which was a very severe flash drought that year. Okay, and you could see that our model over-predicted the yield using the average water productivity harvest index rate. And so we do need to make some research adjustments to the harvest index and take into some of these environmental stressors like drought that are becoming more common out there. So just to finalize where we're going with this is we're have another product called the Global Daily ET product, GLODET. It uses the Alexi model by Martha Anderson from USDA, Chris Hain from NASA as a collaborator, and we're using the VERS satellite, which has the advantage of having the thermal band at the same resolution as the multispectral band at 400 meters, 375 meters. And so with funding from USAID, we implemented this North Africa and Near East region. We use the 2 overpasses to get the rising temperature in the morning, which the Alexi model needs to partition the energy between latent and sensible heat. And Chris Hain came up with a methodology to use the nighttime and daytime overpasses to get that rise. The Alexi runs the 2-source energy balance behind it. I'm not going to go into details. You can read a lot more about it online. And we get daily evapotranspiration at the 400-meter scale. Okay, so you can integrate that daily over the whole year and get an annual ET. And this brings up what Abdul Karim said. This type of resolution would be useful for a water basin or watershed study, right? To look at the water balance, right? And so you'll see that the Nile Basin is a big water user in this particular figure in 2018. Not surprising. It's all irrigated. And we're running it over the Central Plains as well for other projects and studies. And we've compared it against eddy covariance towers. Abdul Karim mentioned the need to compare ET models to the ground truth. So this is at the 400-meter resolution. So that's why you're seeing the scatter. It's due to the resolution. And here against towers in Brazil, which with partners there, we've compared the Alexi ET product down there with good results. And we have a Python version of the DisAlexi model, which disaggregates the Alexi 400-meter pixel to 30-meter resolution using Landsat data. So we can get 30-meter daily AT using this methodology, and that's what Abdul Karim said is needed for to deal with small scale fields that we have commonly in sub-Saharan Africa and other parts of the world. So remote sensing offers a huge opportunity for, as we've seen in this session, for water productivity monitoring of individual scales, fields, and large scales. And so additional research is needed in that conversion of biomass to fiber and grain yield. And we're going to update our water productivity. It's the calculations were until 2014, and we're going to add 6 or 7 more years of data in the next version of this and add additional crops that are important in Nebraska, sugar beet, dry beans, and wheat, and examine also the energy and carbon footprints of how Nebraska agriculture is doing. So thank you. So moving on now for the presentation by Mesfin McConan. It's a video recorded presentation. And
hi, I'm Mesfin McConan, faculty at the University of Alabama and civil
I think
degree.
we have an audio issue.
Fortunately, I was not able to join you because of different reasons, especially visa delays. I hope I'll transfer my the presentation will be clear. If not, if there is some follow-up question, I will leave my email at the end so you can contact me. Let me remove this figure. talk would be the trends in the water productivity livestock products in the US. This analysis was part of a bigger project which I conducted while at the University of Nebraska in the Water for Food Institute. Was part of the 2019 Nebraska Water Productivity Report, where the overall objective was to assess water productivity at different spatial scale, temporal and spatial scale. The work components were the crop water productivity, livestock water productivity, and the water energy and carbon footprint of bioethanol from corn and sugarcane. Today's talk will focus on the livestock water productivity. To give you some perspective, the livestock feed demand globally, it requires about 6 billion tons of dry matter. Out of that, 86% comes from grass, leaves, crop residues, oil cakes, and other byproducts, plus crops or fodder crops specifically grown for as a feed. And the rest 14% is human edible component. This is a small part, but if you focus that's about 1/3 of the global grain production, which is a large amount of feed going to feed the animals or the livestock. What happens in the future? The future also indicates that global meat production and consumption will increase, in particular for the poultry and pig meat. And egg also, beef followed by egg. There will be a large increase in 2050. When we think about this future increase, we need also to think about what will be the resource requirement, what will be the pollution or the greenhouse emission coming from the livestock production and consumption. So one of the reasons for doing this, the livestock water productivity as part of the Nebraska water productivity report, was that cattle production in Nebraska was one of the mainstay of the economy. Nebraska is one of the major beef producer states in the US. Focusing on the whole US, we see that in terms of land use, the livestock production requires about 41% of the land used in the US, especially in the continental US. The larger part, 654 million acres of that, is for pasture and rangeland. Another 127 million acres for producing feed, grains, and other feed crops. Then there's which we eat, but partly goes for animal food. So, as I said earlier, this was at the background of the discussion. Livestock is the major mainstay of the economy in the state, and the feed or the resource requirement is large. We want to see how it has developed over the years in terms of its water productivity, resource requirement, feed requirement especially, and its productivity. While studying the livestock, we studied 6 livestock types: the beef, cattle, dairy, the swine, layer chicken, broiler chicken. There is also a turkey, which is more or less similar process like the broiler chicken. So for each animal type, we try to trace how much animal in each life stage included: a beef, cow, and the producers, the breeders, one beef cow, with 0.04 will produce after including the deaths of small calf, 0.96. That will go partly goes to as a replacement heifer. The rest goes to as a stock. Then as if meat producer. The one which goes as a replacement goes to the as a breeder in the later stage. The same for cattle, dairy cattle. Partly, most of the cows goes for meat production, and when they reach at the end of their life, they are culled and produce meat, swine, chicken, and others. Livestock water productivity is defined as the total amount of meat, milk, or egg production per unit of water consumption. When we talk about water consumption in the livestock sector, we are not only focusing on drinking and the surface water requirement, which is a very minor component compared to the water which goes for producing their feed. The water footprint of the feed account about 98% of the overall water consumption in livestock production. Over the years, we see that the livestock sector has improved. Cattle have become larger, produce more. But what does it mean in terms of their feed conversion ratios? When we talk about the productivity or resource requirement, we need to also see how the feed conversion ratios has developed over the years. Feed conversion ratio is defined as the amount of feed required per unit of animal product, a kilogram of meat, a kilogram of milk, or egg. The feed could be fodder crops, residues, or human edible grains. Yes. 1960, beef cattle used to produce about 270 kilograms of carcass per animal. In 2016, this has increased by 46%, close to 400 kilograms of carcass we get from one beef cattle. A larger animal means larger feed requirement, more trained feeds or grains and other high-dense, nutrient-dense feeds. But the increase in feed requirement compared to the increase in the animal product is less, as we can see. 1960 compared to 2016, there is an increase in of 60% feed per animal. But the increase in livestock product is larger than the increase in the feed requirement, which helps to reduce the feed conversion ratio by 21%. So, and currently, beef cattle or a milk cattle or other animals require less feed to produce more product. Over the years, the animal productivity per unit of animal has increased. In particular, for milk, there we see that 3.8 times increase. In 1960, a milk cow produced about 2.3, 2.4 million grams of milk. 10 grams of milk per animal, 3.8 times. Similar increase, but a lower increase we see for the beef cattle, swine, or pork production, and egg. There is annual variation, but the overall trend is increasing. And the other is the there is a large decrease in the feed conversion ratios for all animals. For beef, there was initially an increase, then a decline afterward. It was annual variation, the overall trend in the animal productivity is increasing, feed conversion ratio is declining. In short, in 2016, fewer animals were needed to produce a relatively large quantity of livestock products. Again, in 2016, less feed required per unit of livestock product. Going to the detail of each animal, the feed conversion ratios, beef is less efficient in converting the feed it consumes to beef compared to the other product, animal types. Milk, egg, chicken, turkey, pork, they have smaller feed conversion ratios compared to the beef. Beef requires about 30 times feed to produce a unit of beef compared to milk or egg. This is in terms of total kilogram, but if we look into the nutrient content, the ratios change, but still we see beef ratio is much larger than the rest of the animals. Why is that? Generally, beef consume less nutrient content feed like grass. The feed composition of the beef is more fodder, grass, or crop residues or other byproducts, while in pork, chicken, it's more grain and high energy dense feed. If we focus on the feed which would have been consumed by human, that's a human edible feed, we see that beef feed conversion ratio change or improved significantly compared to the others, especially if we per unit of protein, edible protein contained in the beef has a smaller feed conversion ratio. It's much better performing compared to the others. So, sure, a low feed conversion ratio may not imply, if we are focusing on the total feed, not imply a low environmental impact. If the beef is consuming more grass from pasture grown by the rain-fed compared to a highly industrialized system of pork or chicken, the environmental impact is totally different, even when the feed conversion ratio of beef is much larger than the other animals. Other animals may have larger environmental impact in terms of water need, water pollution, and nutrient leaching into the water system. So we need to look at the holistic level instead of a single number. Overall, those feed conversion ratio improvement, reduction, high livestock water productivity per unit of animal, improvement in the feed and water footprint has helped to improve the livestock water productivity. For all animals, water productivity has increased over the last 50 years. Reason is that, as I said, improvement in the livestock productivity, output per head of animal has increased. There is a significant decrease in the feed conversion ratio than animals consume less per unit of. Because of improvement in the variety of crops, the fodder crops, the feed crops, there's a decline in the water footprint of the feed. Water footprint feed is the amount of water consumed evapotranspired per yield. So increase in yield has reduced the water footprint of the feed, which has helped together with the other parameters to improve the water productivity of the livestock sector. When we compare the water productivity of the different livestock types, we see milk is more productive in terms of kilogram of feedable product per cubic meter of water consumed. Beef still worse when we look in terms of kilogram of protein produced. The ratio on broad, but still beef is much lower. But this is in terms of the total feed, including the grazing. If we focus on the human edible component and looking at the protein content of the animal products, beef is performing better than the other meat producing and milk products. We're focusing on the meat animals in terms of human edible feed, in terms of protein, even in terms of total kilogram of output per cubic meter of water, beef is doing well. Depending on how we define what's our focus, we need to look at different water productivity types. We need to than a single number. Question is then, we saw a large increase in water productivity of livestock product improvement. Question, will that keep on increasing? The FAO's study shows that livestock productivity will increase or decrease depending on what kind of scenario we follow. In the US, the beef cattle, the business as usual improves stratified system also helps to improve the animal productivity. For milk, all three scenarios show a decline. For pork, it's the message is a mixed, only business as usual. We see an increase in animal productivity. At the global level, beef is doing much better. Pork also, milk still shows a decline. I think the beef and milk increase could be coming from currently a low productive areas of the world, developing and less developed.
Sorry, we were having difficulties with sound, right? What's that? Anyway, I think what we'll do then, this presentation was almost at the end. So we'll jump to question and answers in the last few minutes of the session then. I think Mesfin joined online, but we have the other speakers here. And there's a gentleman with a microphone. So if you have any questions for any of the speakers, please raise your hands and he'll bring you the microphone. And we probably should have the other speakers up front. Yeah, I'm sorry for the difficulty at the end of Messen's presentation. So, any questions out there? Don't be shy. Yeah. There, we can hear that. Yeah.
Is it okay? Hello.
Yeah.
Can you hear me? Oh, yeah.
Yeah.
Yes, thank you. My name is David Agumbome. I'm a PhD student in Delft University of Technology. My question is on the use of remote sensing data to estimate these agricultural parameters or indices in regions where, let's say, rainfall formation has local factors included. Do you think that with less and less weather station on the ground to validate this remote sensing product is still relevant to use them? And what are the ideas in the coming years to filling this gap? For instance, in the case of Africa, if we really want to use remote sensing data to generate information. Thank you.
Go ahead, Livia.
I'll start and then maybe you can complement. Well, I think you touched upon one of the biggest challenges, because we've been saying how difficult it is to monitor water productivity. So to monitor evapotranspiration and biomass and then convert it to yield, and that's all very difficult. But before that, the even bigger challenge is precipitation data indeed. And that's, we sometimes tend to give it for granted, but it's not. And we are aware that many of the satellite-based or combination of satellite with observed data rely on density of weather stations. So indeed, I fully agree with you. And as far as I know, there's just, the only possibility is working on locally calibrated rainfall products and see how they behave if you are working in an area that is subject to local patterns of rainfall. That remains a challenge in that sense. But maybe others have more to say.
Other questions?
Here.
Oh, there's a hand raised over here.
Good afternoon. My name is Aluvoyo. My surname is Gitla. I'm from South Africa. I work as an intern at the National Department of Water and Sanitation. When I was listening, I don't know if I heard correctly, that you use evapotranspiration in order to determine the crop water requirement. When you were speaking on the issue of irrigation, where the farmers meter their water in order to determine how much water they use for their irrigation purposes. So I wanted to know, how then do you measure the water in terms of each crop, because they're obviously not going to plant the same crops. So how then do you determine the crop water requirement for each specific crop, and then in order to determine the type of irrigation system that they should use in their farm?
Okay. Can you hear me? Yeah, this is one of the issues I raised earlier. We need to have an accurate crop map. Land cover map is absolutely important, because you want for example, if you want to convert the biomass production into yield, you use factors which are crop dependent. For this reason, actually having a validated or accurate crop map is very important. But there's an issue. Sometimes there's intercropping. All right. When you have intercropping, then you have more than one crop in the same farm, in the same field. Then obviously inevitable that the actual water use you have estimated will be for that farm without the different types of crops. But usually if you have one type of crop, probably it is easier to get, I mean, like an accurate land cover map based on ground surveys, for example, and that can help you to determine how much water being used for this crop because you have one. But when you have intercropping, mixed cropping, then obviously it's a big challenge. Probably, in my view, any estimate you make is for that particular farm, covering all the types of crops.
Can I just maybe add to that? I fully agree with Karim, but I also think that is maybe one of the situations in which we can make good use of smartphone applications in certain conditions. So, for example, there are apps that in which the farmer they can input what crops they are growing, and then with that information and the combination of remote sensing information, you can get a more tailored advice. Of course, this solution doesn't work everywhere. It depends on what type of farming system, farming community you have, but it might be a solution in some cases.
Looks like we have another question.
Hello. Thank you very much for the talks. They were really interesting. Very connected question. I was wondering how you plan to analyze agroforestry. I noticed that the water productivity in a lot of the Sahel in your map was very low, but there's also a lot of parklands in that region, and that's all evapotranspiration that's happening without any sort of agricultural biomass being extracted. But the productivity of the crop that is there per the water that those crops are using is probably pretty high. So just was wondering how you plan to analyze that.
Well, I don't know. I'll just say one thing, and then I think that links very much to the definition of water productivity. Also, no, we've seen that there's many dimensions to water productivity, and agroforestry is definitely a case where the definition of water productivity goes beyond biomass per unit of water consumed, because there's a lot of additional benefits to agroforestry that are not quantifiable directly through biomass. No, so that is one of the situations in which, the multiple dimensions need to be looked at, and working with on the ground is the only way to get those dimensions. But maybe other speakers have more ideas.
Well, I think, the WAPOR product, right? You're getting ET in the crop areas. You'll get ET in the forest areas as well, right? It's
if they're mixed, of course, it's
then
complex.
if it's mixed, it's complex, right? Do we have other questions?
If there's no other question, just want to add one thing. If there's no other question, I would like to add to the answer we gave to the PhD student on rainfall. That's a very important question. I just want to highlight to alert you about, we have a recent publication where we compared quite a number of rainfall products using ground observation to validate. And it's really not straightforward, really, because it depends upon the time scale, the spatial scale. So for this reason, I think you need to see different factors when you compare different rainfall products, even having ground observation, because ground observations normally are point observations, all right? But satellite observations or estimates are really spatial estimates. And there's also an issue of the type of rainfall, rainfall formation system and so on. So you need to look into all that. And there's a publication, which probably I will be very happy to share information about that. Yeah, you need to look into that kind of issue. Thank you. Just want to add this one.
Thank you. I think we are out of time. Thank you all for participating. Thank you for the speakers for their presentations, and hope to see you next time. Thank you.
Thank you.